Alright, so Latin squares in engineering. First off, what are Latin squares? They're tools used in ANOVA, or the analysis of variance, when two nuisance factors are to be eliminated from the error variability. In other words, when you need to control two sources of nuisance variability, you can do so simultaneously with a Latin square. Why Latin squares? The name comes from the Latin letters that are used to name the corresponding treatments of variation. In fact, the number of treatment factor levels correspond to the amount of rows and columns. And there's an underlying assumption actually, which is that the nuisance factors are independent of all other factors. And that's why they're called the nuisance factors. So what is ANOVA? ANOVA stands for the analysis of variance. It is used to understand the dynamic effect that factors have on the variance, the total variance of the experiment. A simple example is the order effect, where a preceding factor has an effect on the factor that comes after it, just because of the order. In engineering, Latin squares, we deal with controlling nuisance factors. So we set up a series of formulas and treatments. We test for the nuisance factors, and then we eliminate the influence on the process from those nuisance factors. Basically, what you do is you go from row and from column, and the same letter cannot repeat itself. You create an alternating sequence of the letters which represent the treatments. So what is the application of Latin squares, for example, in engineering and in aerospace engineering? Well, in aerospace engineering, such as any other engineering field, a multitude of influencing factors present themselves. One example that we're going to present is the application of Latin squares in choosing the correct rocket propellant. So when we're taking this into account, we want to optimize the fuel. We take the nuisance factors of the operator and the batch of material, which should not affect our experiment. They're nuisance factors, they're independent of the outcome. We try to minimize them by running the different formulas 1, 2, and 3 through the process that analyzes the effect of the operator and batch of material to end up with a process that minimizes the influences from the operators and batches of material. With A, B, C, D, and E being the fuel formulas, the batches of materials being laid out here, and the operators being laid out here, we compare the variability, which we've got results for, being a practical experiment in real life. And we would see which combination of operator and batch of material minimizes the variability.